This classroom lesson is a cooperative effort between the Wisconsin Public Service SolarWise for Schools program and the Create Energy Center. This is Lesson 5, The Solar Window. Introduction and Lesson Objectives. Welcome students and teachers to What's on Our Roof, a series of lessons in which you'll learn from the photovoltaic performance data produced by your solar array. This is Lesson 5, The Solar Window. In this lesson, you'll understand the importance of maximizing solar electricity generation within the solar window. You'll determine the ideal electrical output from your solar array during the solar window, and you'll measure the actual electrical output produced by your array during the solar window. The solar window and its importance. You were introduced to the solar window in Lesson 2, so now it's time to become better and more fully acquainted with its definition. The solar window is the critical hours of 9 a.m. solar time to 3 p.m. solar time that are the most important for the conversion of sunlight into electricity for a well-positioned, fixed solar array. In this picture, I'm taking a panorama photo from behind a relatively small, fixed, well-positioned rooftop solar PV array. This array. As you know, the panorama setting distorts a photo, but it gives us a picture showing a much wider sweep of sky in front of the array, like this. Let's imagine a cloudless day in front of this array on the first day of spring and fall. We'll imagine the sun follows this general path as it moves across the sky on the first day of spring and fall from this reference point. At this location, which is roughly 45 degrees north latitude, the sun rises almost due east on the first day of spring and fall. Of course, due east is 90 degrees on the compass dial. We say that the sun rises at an azimuth of 90 degrees. Here on the first day of spring and fall, the sun sets at almost due west, an azimuth of 270 degrees on the compass. Splitting those two extremes exactly in half, the sun will be due south in the middle of the daylight hours, an azimuth of 180 degrees. We call this interesting location and time solar noon. The sun is always due south at an azimuth of 180 degrees every day of the year at solar noon in the northern hemisphere. The sun is also at its highest point in the sky every day at solar noon, its maximum altitude or its zenith. At this location on the first day of spring and fall, that altitude is about 45 degrees high in the sky, the angle from the horizon to the center of the sun's disk. And finally, at this location on the first day of spring and fall, there are almost exactly 12 daylight hours, 6 hours before solar noon and 6 hours after. Naturally, we can also define the path of the sun across the sky at this location for the first day of summer. Note the changes in azimuth for sunrise and sunset. But notice the azimuth at solar noon doesn't change. It's always 180 degrees or due south. Also note the sun's path is drawn higher in the sky. For this location at solar noon, the altitude of the sun is the highest of the year, at about 70 degrees. And look how much more daylight we get on what most people call the longest day of the year. In a similar way, we can trace the sun's path across the sky on the first day of winter for this location. We won't take time to point them all out, but look at all of the changes for the shortest day of the year. Here we've placed all 3 sun paths for the first day of each season on the same slide. Let's clean it up a bit. Then we'll mark 9 a.m. solar time and 3 p.m. solar time on each sun path. By our definition, these times mark the beginning and the end of the solar window. Connecting the dots, we get a pictorial representation of the solar window in the sky for this location. The critical hours of 9 a.m. solar time to 3 p.m. solar time that are the most important for the conversion of sunlight into electricity for a well-positioned fixed solar array. So why are these 6 hours the most critical? Why do they usually provide the majority of the day's energy for a well-positioned fixed solar array? Most of us understand intuitively that sunlight is stronger during midday hours. An hour in the sun in the early morning or late afternoon treats us much differently than an hour of sun in the middle of the day. But why is this so? When the sun is overhead around midday, its rays travel the shortest distance through the atmosphere to reach the Earth's surface. This minimizes the amount of energy lost through absorption and scattering by atmospheric gases, clouds, and particles. Around sunrise and sunset, sunlight must pass through a much thicker and longer section of the atmosphere. The longer path through the atmosphere increases the amount of solar radiation that is absorbed and scattered. This significantly reduces the intensity of the light that reaches Earth's surface. Also, when the sun is high in the sky around midday, its rays strike Earth's surface at the most direct, perpendicular angle. This concentrates midday solar radiation over the smallest possible area, resulting in the most intense sunlight. But in the morning and late afternoon, the sun is lower in the sky and its rays hit Earth's surface at a more slanted angle. This causes sunlight to be spread out over a larger surface area, and that decreases the intensity of solar radiation at any one point. For a fixed solar array, one that does not move with the sun, this combination of factors means it produces its maximum output during the middle of the day, during the solar window. From this, a natural question arises. What should be the ideal solar production in the solar window? What portion of the day's production should take place there? To answer that question, we turn to the Solar Pathfinder. The Solar Pathfinder is one of a number of tools that may be used by solar professionals to determine if a specific location may be suitable for the installation of a solar PV array. It's portable, it's non-electric. Properly used, it takes into account the shading patterns at a specific location throughout the entire year. And it's worth a mention that we have a separate, excellent, and fun classroom lesson available on using the Solar Pathfinder. It has a base, on top of which is placed the instrument section, which has a leveling bubble and compass, which are both used for proper orientation at and on the site being surveyed. Onto the instrument section is placed a sun path diagram, which you'll learn much more about in a moment. On top of and working with a properly oriented sun path diagram goes a curved, reflective dome, all of which enables a user to take into account the shading patterns throughout the entire year to determine if a specific location may be suitable for the installation of a PV system. As you can plainly see, with numerous trees shading the dome, this would be a bad place to locate a solar PV array. But this spot is an improvement. There is shade covering the sun path diagram only on the very edges of the reflective dome. That means the rest of the sun path diagram, where a solar array might be assembled, is open to the sun the rest of the year. But how do we interpret this with precision? Let's take a closer look at the features of a sun path diagram placed just below the reflective dome on the instrument section. First, there are different sun path diagrams for different locations. This one may be used anywhere between 43 and 49 degrees north latitude, where the daily path of the sun across the sky is similar. You can see here how the sun's path is different depending on latitude. Months of the year are associated with each of the 12 arcs on the sun path diagram. Each arc visually indicates the average daily path of the sun for the month. The time of day, in solar time, is shown along the bottom of the diagram. And each hour of the day is divided into 30-minute time segments. The percent of sunlight available within each 30-minute segment for an average day of the month indicated is given along the sun path arc for each month. Since the sun path diagram shows time in solar time, solar noon is shown right in the center. Solar noon is the moment during the day when the sun reaches its highest point in the sky, its maximum elevation, or zenith. This is also the moment during the day when the sun is due south. Its azimuth is 180 degrees on the compass dial. At this moment, the length of time from sunrise to solar noon is equal to the length of time from solar noon to sunset. Solar noon is usually close to, but is seldom the same as clock noon. The solar window can be readily identified and visualized too. The solar window, the definition used most commonly in the solar PV industry, is the critical hours of 9 a.m. to 3 p.m. that are the most important for the conversion of sunlight into electricity for a well-positioned fixed solar array. Now that you know how to interpret a sun path diagram, let's perform a solar PV site assessment, the old school way. First, the pathfinder is positioned, oriented, and leveled on the spot where a solar PV array is being considered for placement. The boundary between shade and sun, visible on the reflective dome, is traced on the sun path diagram below it. Recall that the sum of the numbers across each monthly arc is 100. Each number indicates the percentage of sunlight available during a 30-minute time segment for an average day of the month indicated. And since there are 12 arcs, one for each month, that means the sum of all the numbers on the face of the sun path diagram is 1200. Go back to your tracing and add all of the numbers on the diagram that are open to the sun. Let's say this is your number. Now there's just a little bit of math, and here's the percent of sunlight that will be open to an array at this location for the year. 96% would be a real good number, by the way. Showing you how the Pathfinder works should suggest how you can quantify the ideal electrical output from your solar array during the solar window. Your teacher will have you pick a month from the appropriate sun path diagram. I like March, so I'll use it in this example. The sum of the percent of an average day's sunlight for the month along the arc will naturally equal 100. Add all of the numbers within the solar window. The percent of energy that will be generated during the solar window on a sunny average day of the month is the percent of energy that will be generated during the solar window over the percent of energy that will be generated over the entire day. times 100. And you've got it. Do this correctly, and you'll have determined the ideal electrical output from your array during the solar window. So now it's time to compare this ideal electrical output in the solar window to the actual solar window production for the array you're studying. Navigate to the eGauge web portal for the solar array you're studying. Enter the first day of the month for the month your teacher assigned you. You'll be advancing day by day throughout the month, looking for the day with the highest output, which will also be the day with the most sun throughout the day. Why are we looking for this kind of day? Because we'll be comparing actual solar window production for this kind of day to the ideal solar window production we calculated earlier. The sun path diagram from which ideal solar window production was calculated assumed ideal conditions of orientation and full sun all day. Keep advancing day by day, looking for the day with the highest energy output. When you've found that day, record the energy generated for that day. In addition, take a screenshot or snip of this output profile to copy into your student guide where indicated. Go back to reset the time period for that day. Reset the time period to the solar window, 9 a.m. to 3 p.m. You may have to adjust for daylight savings time. Record the energy generated during the solar window for the day. Then, take a screenshot or snip of this output profile to copy into your student guide where indicated. To determine the percent of energy generated on the best day of the month during the solar window, take the energy generated during the solar window over the energy generated during the entire day, times 100, and you've got it. In review, in Lesson 5, you've learned about the solar window, how to establish ideal output within the solar window, and how to determine the actual output within a solar window. Now, complete additional work for this lesson, then move on to Lesson 6 of Watts on Our Roof.